Hello everybody, my name is Marcusringstro and I'm a PhD student at KTH at the Division of Applied Electrochemistry, and this project is in close collaboration between KTH and PowerCell Sweden AB. So in this short presentation I will go through the background, research objectives, approach, and what results that might be expected from this project. I will share my screen. Yes, so the title of this project is Fuel Cell Performance Prediction. And as I mentioned before, my name is Marcusringstro. I'm a PhD student. And my supervisors are Professor Rakel Vreeland Lindström, KTH, co-supervisor Göran Lindberg, Professor KTH, and Dr. Lisa Kylhammar, PowerCell. What is the background? Well, the gas diffusion layer of a PEM fuel cell plays a vital role, as its function is to provide a pathway of reactants and liquid water removal. And liquid water removal in the porous layer has a detrimental impact on performance of a PEM fuel cell. And the GDL also have to ensure good electrical and thermal conductivity, as well as serve as a mechanical support for the MEA, or the membrane electrode assembly. These functions impose requirements of mechanical and electrical properties such as gas permeability, water management properties, electrical and thermal conductivity, and chemical and physical durability. It is therefore important to couple these effects on the compression to get a thorough understanding of the complex interactions and thus be able to ultimately predict the fuel cell performance. So what are the objectives? Well, the goal of the project is to develop experimental and modeling tools to study and optimize stack performance, and specifically study the impacts of varying porosity, vertability, capillary fingering, and mechanical properties, as well as electrical and thermal conductivity of the gas diffusion layer, stack compression and flow field design, humidification, and other operating conditions at various drive cycle situations. So here we have a picture of a commercial fuel stack from PowerCell, the S3, with the power output of 20 to 125 kilowatts, and a schematic picture of the assembly of a fuel stack with the noted components. And the approach is so through experiments and modeling, make a material characterization of the GDL to be able to predict fuel cell performance. The model should be able to predict performance based on effective parameters gained from ex situ and in situ experimental methods and modeling techniques. And here we have a schematic of the approach. So we begin with carry out the material characterization. So we find the electrical parameter, the thermal conductivity parameters, mechanical parameters such as in-plane, through-plane, Young's modulus, shear modulus, Poisson's number, and the diffusive parameters as a function of compression. From these parameters, I will couple them into a 2D finite element method model, and hopefully be able to predict performance for a variety of flow field designs. So what results are to be expected? To get a deep fundamental understanding of the needed characteristics of the GDL, and to identify and implement necessary tools to measure the relevant material properties, and have a capable model for the prediction of the PEM fuel cell MEA performance, and through, of course, research publications and presentations at national and international conferences that will lead to a PhD degree. So I've included some pictures of the porous DDL from a SEM scanned electron microscope, as well as the influence, how the contact resistance is influenced by an increase in clamping pressure. So this is just some examples of results that might be expected. Yes, and thank you all for listening to this, and hope you found it interesting. And if you have any questions, don't hesitate to contact me. Yeah, thank you for your time. Bye.